All right, so this is the second extension that we're going to do today. So we already talked about tires and tread wear and how that affects the speedometer. Now we're going to get into time zones. So this is totally starting to get into spherical geometry, which is non-Euclidean. We've talked about this a little bit. In fact, at the beginning, we're going to talk about the world, of course, and the world's flat. So spoilers, I know. Trigger warning. The world's round. Did I say it was flat? Oh gosh. Oh wow, I'm so messed up. Anyway, so we've talked about this before. One of the things that is an important concept that we'll get into today is the great circle circumference. So there are many. Imagine you have an orange. There are many ways you can slice an orange in half, right? But let's say that you slice it in half so that it's cut into two equal halves. Well, that circumference that's formed when you cut it exactly into two equal halves is called a great circle circumference. And you can cut it from any direction and find a great circle circumference. In fact, between any 2 points on the orange, there's exactly one great circle circumference that goes through it. And what's fascinating is that great circle circumference is the shortest distance between those 2 points. And so we actually deal with these quite a bit in navigation because, of course, the world's not flat. So a lot of our Euclidean geometry, which is just totally where we're dealing with planes that are flat and not curved surfaces, right? A lot of it kind of breaks down. And so we're going to kind of investigate that a little bit today. And we've talked about the curvature of the Earth with tangents. We'll talk about that again on Friday with Columbus. So a lot of really cool stuff here. And this is really high level things that we're getting into. Also, I'm going to share a resource, a really cool website that you can plot 2 points. And it'll show you on Google Earth the distance between the 2 points and the haversine functions and stuff like that. So it's really, really cool stuff. I am really excited to show you this. So I'm going to stop talking. That was 2 minutes. But hopefully you heard all that because it's really good. All right, so how many time zones should China have? So this is China. I usually go to China, but every summer. But because something special happened in Wuhan this summer, I'm not going to be able to go. But usually when I go, I might as well show you, I go to Guangzhou. So Guangzhou is right next to Hong Kong, which I've only been in the airport, and Macau. And I did a visa run to Macau once because I almost overstayed my visa by a day, and that's not cool. So other things, I've been to Chongqing and Chengdu, and never been to Xi'an. That's the old capital, but I have been to Beijing, and that's pretty much it, and some small towns around Guangzhou. But yeah, fun stuff. Really missing my friends in China, and yeah, I'm not gonna be able to go back till next summer, so that really stinks. All right, so how many time zones should China have? Well, an odd fact about China is that they only have one time zone, Beijing time. So Beijing's their capital, their former capital was Xi'an. That's where all the buried soldiers, the buried army is, and stuff like that. Chengdu, it's where the pandas are from. And Sichuan province are known for spicy food, so cool stuff. Anyway, but yeah, Beijing time is the same time for everyone else. So it'll be kind of like in the U.S., everyone running off of Eastern time. And the United States actually has 6 time zones because Alaska and Hawaii have their own time zone. But then you got the 4 for the main 4 that you already know, right? So Eastern, Central, Mountain, and Pacific. All right, so China is actually 14 hours off from us. They're 13 right now during the summertime because we are on daylight savings, but typically they are 14 hours, so they're ahead of us. Yeah, 14 hours. It's pretty cool. All right, so first question is, how many hours are in a day? Not a trick question. 24, right? So it's not exactly 24, but we like to go with 24. So then how many time zones should we have? Well, the whole point of a time zone is that we can set the times off by 1 hour, depending on where you are, so that the sun rises and sets at kind of a standard-ish time, so that we don't have the sun rising at noon or something like that, which would be kind of extreme. Or is it? So how many time zones should we have? Well, if we have 24 hours in a day, we should probably have 24 separate time zones. Well, we don't. The world's not ideal. We actually have 37 different time zones. The reason for that is there are a lot of islands that have like half time zones, so like a 30-minute instead of an hour difference between one and the other. There's also some that are 45 minutes off of what we would consider a standard time zone going off of GMT. So Greenwich Mean Time, I think is what that means. Anyway, so which is an observatory in England. So anyway, lots of cool stuff to share with you guys today. So yes, 37 different time zones in the world. We would think ideally we would have 24, but there are a lot, like the Australia, I believe, has 3 time zones, and the time zone in the middle of the, so kind of like their central time or whatever, is 30 minutes off from the East Coast and the West Coast, which is really, really interesting. All right, so the question I have is, if we have 24 time zones, so I'm going to go ahead and get rid of this so it doesn't confuse us, but if we have 24 time zones, then how many degrees should we go for each hour? So if we're breaking up these lines of longitude here, right? So from the prime meridian, 15 degrees, 30, 15, 30, 45. So how many degrees should we go over to break up each of our time zones? If we're, kind of ideally speaking, we're not going off of, geographical locations and political boundaries and stuff like that, but we're just going off pure degrees. Well, the way we do this would be 360 degrees, because that's how many degrees we have in our circle of altness, divided by 24 hours, and that will give us 15 degrees for every hour. So, in other words, the Earth rotates 15 degrees relative to the sun for every single hour, which is interesting, because then in full 24 hours, it'll have a full 360 degree circle of altness. So pretty cool. So every 15 degrees you see here, that would be another time zone. So you can see in the States, we kind of have our Eastern time, Maine's kind of on its own. Then we have Central, then we have Mountain Time, and then Pacific on the back. Then you have Alaska, and then Hawaii is going to be an hour after that. Okay, kind of cool stuff. And that's our time zones. So here's China and China's time zone. So from the Greenwich Mean Time, they're 8 hours ahead of that, I believe. And that's Beijing, which is right here. So if the sun rises at 7:05 in Beijing, that would be like in the winter. Actually, I just looked it up, but right now, like the sun in the summer rises at like 4 o'clock in the morning, which is crazy, because they're just right over. The sun's really centered on them, so they have a lot of daylight. Anyway, so if the sun rises at 7:05, then what time would the sun rise if you were in Western China? Now, most of their population, of course, lives on the East Coast, but there are people who live out kind of in the desert of Western China. I actually knew somebody who was from one of those countries over there, which is actually kind of cool. So if it rose at 7:05, then each one of these, if we see as it goes over, that's going to be 120 degrees east. So each one of those is 15 degrees, which is a separating by 1 hour, right? So that would mean that they would have to wait for the sun to rise at 8:05, 9:05, and then 10:05, so they would be 3 hours off. So if you can imagine, the sun doesn't come up until 10:05 in the morning if you're in Western China. Also, if the sun would set at 7 o'clock, for them, that the sun would be up till 10 o'clock at night, which is crazy. So it might be convenient having one time zone, but for the people who live in the West, it's kind of crazy. Also, if they're crossing the border and trading with somebody or something like that, more than likely those countries are going to be 3 hours. Their time zones are going to be 3 hours off from there, so it would get a little confusing. But I'm sure they figure it out just fine. So anyway, how many time zones should China have? Well, we can see it actually breaks down kind of nice to 1, 2, 3, 4. So just like the U.S., about the same width of the U.S. as well. They should have, if they were doing it ideally, they would have 4 different time zones, but they actually only have 1. All right, so that brings us into latitude and longitude. So got some pretty cool graphics here. I totally remade this. I don't think I updated it on yours, but hey, I can do that. That's fine. So on this one, the first thing I'm showing is our lines of latitude. So we also call these the parallels. So first we have the equator, which is at 0 degrees latitude, and then 20 degrees north would be the 20th parallel, right? Then 40 degrees north, 60, 80, and then the very top North Pole would be 90 degrees north. So you might be able to guess how they're measuring these degrees out. Well, it's the angle that comes from the center, right? So from the center of the Earth, going from the equator going up, that's the angle that's swept out. So 90 degrees would be the North Pole, right? Okay, then you also have the degrees south as well, which they sometimes they use negative numbers to denote those. Also, they'll just say like 40 degrees south. Works just fine. Okay, so those are lines of latitude. I remember the difference between latitude and longitude is kind of crude, but I like fatitude, so width. So the lines of latitude, they go wide. My brother told me that. I know I shouldn't have shared it, but it works. All right, so then we have lines of longitude. I know that is so awesome. All right, so the lines of longitude they're actually longer as well than some of the lines of latitude. So if we go back, we'll go back real quick. So with the lines of latitude, this is one of the questions that you're going to have, is that you notice as we go higher and further away from the equator, we're no longer the great circumference, right? So the biggest circumference that we can get cutting the Earth exactly in half would be the equator or prime meridian, right? But there are many, many of those, by the way. But as we keep going further north or further south away from the equator, the circles get smaller, and they get so small eventually we get to just a single point, right? Which is kind of cool. And the same thing would happen down here in Antarctica as well. So as we go up in longitude, and if we're following a parallel, which is why we never navigate following parallels, which is really cool, we always follow the great circle circumference. Anyway, the radiuses are going to shrink, and we're going to have to adjust that in our work today. Then we have lines of longitude, which of course are the ones that are going north and south here. So I can't click anywhere until that goes away. All right, so lines of longitude, if you notice, those do not change. So we start out the prime meridian, which is 0. Then we have 20 degrees east, 40 degrees east, and it goes all the way around. Then we have 20 degrees west, 40 degrees west, etc. So west would be considered, I believe, a negative number because it's like the quadrant. So we have first quadrant here, second quadrant, third quadrant, and fourth quadrant, centered at around the Mediterranean Sea, right? So Greenwich, which would be the United Kingdom, and then just over Africa. So this is probably right around the Strait of Gibraltar or Morocco, if I had to guess. Anyway, so that would be kind of our origin. Anything else I need to say on this one? I don't think so. So you've got some examples you can go through here. And I guess I got more stuff to show you. Oh, yeah. So if we wanted to go to this point right here, and we wanted to name the latitude and longitude. So first we would say the latitude. So how far up are we going? Well, we're on the 40th parallel. So that would be 40 degrees north. And then our longitude would be how far over west we're going, which would be 60 degrees west. So 40 degrees longitude, 60 degrees west. So 40 north, 60 west. Also, once they break down degrees, they usually don't use decimals of a degree. They start doing minutes and seconds. So it would be out of a 60th, right? So you might be 60 degrees, 4 minutes, and 5 seconds, which would mean 4 out of 60 degrees. And then after that, you would get into seconds, which would be another 60th of a 60th, which would be a 3,600 or whatever. So anyway, more cool information that you probably aren't used to hearing, but that's what this whole thing's about. So I'm going to show you all this extra stuff. All right, so this we said would be 40 degrees north and 60 degrees west. All right, so here's some points you can practice plotting these out. So the point A here, that you will notice, see again, we've got our origin. Wow, I thought it was way up here. Apparently the equator, I was way off there. Yeah, good try. Apparently my geography is a little rusty. So for the point A, the point I was trying to get at before is that you'll notice that when we order the pairs, and when we write them as ordered pairs, we actually do it backwards. So we do the latitude first, which is going to be the parallel. So this is going to be the 75th north for latitude, and then the longitude, which would be like the x component, is going to be 0. So you would think you'd write this as 0 and 75, but you actually write it as 75 and 0. So it's backwards from like the x and y coordinates that we're used to. So that would be point A. Point B is latitude of 15, longitude of 60, it looks like. We would do either 15 north, 60 west, or you would do 15 and then negative 60 because we're going in the negative direction over here because we are in the second quadrant, essentially, if you're looking at that. So you can do the rest of those just for fun. They're kind of cool. All right, so 4A. So estimate the height of China. So over here, we've got 2 points. So the highest point of China is along the 53rd and a half parallel. And then the lowest point near Hainan Island here is going to be 18 degrees north. So we want to estimate what is the actual height of China. So when we're doing this, I can actually graph those points out. Do I want to show that to you now? We'll do it at the end to like check our answer. All right, so for the height of China, we're going from 9 degrees north to 58 degrees north, so these two parallels, and all we have to do is find the physical distance between those two parallels. Well, looking over that in 2D, so it's 3D, then over 2D, I just kind of like did a vertical slice, right? We have the smaller circumference at the 53rd and a half parallel, and another smaller one that's at the 18th parallel. We just want to know the distance between these two. Well, if we subtract those 2 degrees, because those are both measured from the angle of elevation from the circumference, we subtract those two angles, that'll tell us the angle in between them, difference between the angles, which is 35.5 degrees. So then what we end up with is a sector where we want to know the arc length of this arc, this section of, or this arc of a circle. So we use our arc length formula, which is the fraction times the whole. So to get this is going to be the entire circumference of the Earth, which we're going to use it more precise than 6,400 kilometers. We're going to use 6,380 kilometers in this case. And then our fraction is going to be our 35.5. So I'm just going to show you the work for this one. We plug all this in our calculator and we end up with a height of 3,953 kilometers. Now that's our estimate. I'm going to show you a really cool site. So the link is, I put it on Google Classroom, and I think I put it on one of these slides in here. You'll see as well. So anyway, this is, I think the site is from the UK or something. That's probably why they're showing this. But you can put your 2 points plotted here. They tell you the different ways you can put it in. This would be 40 degrees, 44 minutes, and 55 seconds. I'm actually just going to put it in as a decimal. You can also use positive and negatives as well. So I'm going to put in the first point here. So let me scroll over here. Give me just a moment. So the furthest point north in China is going to be 53.5 degrees north. So that's just going to be positive, but if I want, I could put in with it for north. And then the longitude for that would be 123, which again is just positive. So you can watch it, graph it out, and update it, which is pretty cool. And then the furthest south is going to be 18 and 110. Boom. So check that out. You can see the points, make sure you got them right and put them in correctly, and then it'll actually give you the information. So it'll calculate the distance, and you'll start noticing that this distance here, it's of course a great circle circumference. Think about cutting that orange exactly in half. And so it's always a curved distance, not a direct, as the crow flies, is actually going to show up curved on a two-dimensional map like we have here. So pretty awesome. In this case, the actual distance was 4,100 kilometers, and our estimate was about 50 kilometers less than that. So really close. The reason it was a little bit different, let me go back to this if I can. The reason it was a little different is because we're not only going straight up, but we're also going to the right as well a little bit. So if I change one of these to, let's do 123, then our estimate is going to be a lot closer. So you notice how we're going exactly straight up. So 1947, and yeah, that's within 5 kilometers. And the difference we're seeing in that is exactly because we used a rounded value for the radius of the Earth. It's actually more precise. I think it's 6,378 kilometers or something like that. So if it would have updated that slightly lower value would have caused this to be different and would give us the exact value that they got here because those were lined up exactly along the same line of latitude, which is really cool. Okay, so height of China did that. That's actually the easy part. Now let's look at the width of China. So we're 20 minutes in. Man, I just can't stop talking all the cool stuff I'm trying to show you. That's why I'm breaking out in 3 different videos, so I don't feel bad about it. All right, so width of China. So we have our furthest west point, our furthest east point over here, and we want to know what is this distance between the two. Now notice here I'm showing these are not straight lines because we're talking about a curved surface here. So we're going to go along the 45th parallel to estimate what we think that distance is. So if we did it along the 40th, it would be too long of an estimate. And so we're going to go up to the 45th parallel, which is about right here. And we're going to find out how wide from that degree 74 east all the way to 135 if we traveled along the 45th parallel. Okay, so we're kind of splitting the difference between those two. All right. Yeah, that's all I need to say. Okay, this is the website in case you were wondering where I was able to show this stuff. So, all right, width of China. So we're going to go up to the 45th parallel and travel a distance along the 45th parallel. So the first thing we notice is that the radius of the 45th parallel is not the same as the circumference of the Earth. It is less, right? Because as we travel further away from the equator, it's no longer a great circle circumference, and so we need to change that. Well, this value here is going to be the exact same as this value down here. So what we end up with is a right triangle. Our hypotenuse is the radius of the Earth, and to find the adjacent leg, we just have to use trig. Well, we're on the 45th parallel, which means this angle is 45, so we use the cosine adjacent to hypotenuse, right? Adjacent over hypotenuse would be x over that. We multiply both sides by, 6,380, which gives us a distance of 4,511 kilometers. So that is our estimate for the radius. That's not the distance we want. We've got one more step to do. But that's our radius. So notice our radius is shorter now. We're going from 74 east to 135 east. So if we subtract those two, that's 61 degrees altogether. We want to know what's the physical length with the central angle of 61. Notice now we're no longer using the radius of the Earth because we have a shortened radius at the 45th parallel, which we found on the other step. So we just plug in our arc length formula, which will give us an estimated distance of 4,803 kilometers. Now I'm going to put in these values into our cool thing here. If tab, I can go back. All right, so westernmost point is at 39, and I can put these all in as positive values because we're in the first quadrant, which is really helpful. And then the easternmost point is 48 and 135. Okay, cool. So you can see we're all the way from Western China to way up near Russia. All right, so our actual distance that we found using the haversine function, or they did for us, is about 4,889. Our estimate from using the 45th parallel, really close, within 86 kilometers. That's not bad at all. Like, that's really impressive. Now keep in mind, when we were doing this, we were just taking an estimate. So if we would have went along the 40th parallel, it would have been too long. If we went higher than 45th, it would have been too short, right? So we just kind of guessed about 2/3 the way up, and it worked out pretty well. All right, moving on. No, that's it. Yeah, so last thing we're going to use is going into talking about Christopher Columbus and the distance that he traveled. We know where he started and we know where he landed, or we estimate somewhere in the Bahamas where we think he landed. And we're going to see if we can use the Pythagorean theorem just from our Euclidean two-dimensional surfaces and planes and stuff in order to estimate how far he traveled. And we're going to use our new cool website that we found to actually find out the actual distance as the crow flies that he would have traveled and see how close we get. All right, so I will see you back at the next video. Sorry this one went a little long, but I hope you guys are enjoying. This is really fun for me. This is cool math, and I get to show it off with you guys. So I'll see you.